GeoSynth, a photorealistic synthetic indoor dataset for scene understanding. Many augmented reality applications, such as the removal of real furniture from a scene, rely on advanced computer vision algorithms and deep learning models. With state-of-the-art methods, critical elements of a scene's lighting and geometry can be estimated to allow for the realistic insertion of virtual objects. To train a deep learning model, we need an annotated dataset that maps given inputs to outputs we would like to predict. Conventionally, datasets are created by gathering a large number of images relevant to a desired task and having human annotators painstakingly label the data. Not only is this expensive, tedious, and time-consuming, it's also an error-prone process. An alternative is to create a computer-generated synthetic dataset to reduce the need for expensive human annotated data. In this paper, we present GeoSynth, a photorealistic dataset aimed for training neural networks in the task of indoor scene understanding. Concurrent with our work, other photorealistic datasets like HyperSim and OpenRooms have been developed. Both are large-scale, detailed datasets with large scene variability and available ground truth annotations. For instance, HyperSim contains 461 different indoor scenes that were sampled along a camera trajectory to generate 77,400 images. On the other hand, OpenRooms took a different approach to scene generation. Rather than relying on artists digitally creating a scene from scratch, they took real 3D scans from ScanNet and developed a semi-automated toolset to rapidly create a fully digital scene equivalent. Using this technique, they generated over 100,000 exemplars that better represent the layout and contents of real rooms. Our work is complementary to these synthetic datasets. The GeoSynth dataset and associated tools aim to generate a diverse set of label-complete, photorealistic indoor imagery of typical homes as quickly and as inexpensively as possible. The process of creating any large-scale dataset starts with room acquisition. We want to gather as many scenes as possible that contain high-quality materials and textures and are representative of real-world residential homes. We sourced our assets from IKEA's 3D catalog, public Blender marketplaces, and developed some additional assets in-house. Our goal is to generate hundreds of label-complete variations of a room from a single standalone Blender file. To maximize the number of ground truth packages generated from a room, we introduced the concept of a variant using Blender collections. We consider 4 types of collections: cameras, lighting, materials, and layouts. Each of these collections is automatically built using heuristics. Most existing synthetic datasets required large amounts of tedious and expensive manual work. We optimized this process by developing an in-house annotation tool that enables rapid object labeling, lighting modeling, and scene debugging. With this toolkit, we are able to efficiently render over 18,000 exemplars from 36 distinct rooms at a fraction of the cost compared to other similar datasets. Each exemplar contains an RGB render of the scene and 20 ground truth assets, categorized into 4 main groups: camera intrinsics and extrinsics, geometry attributes like depth maps and surface normals, instance and semantic segmentation labels, lighting models and assets like environment maps and image intrinsic decomposition components. The generated data is intended to simulate a typical IKEA customer taking a photo of their room. Therefore, the dataset statistics should be similar to our target application domain. For example, in GeoSynth, the average camera height is 1.32 meters, and the average depth value is 4.45 meters. A comparable dataset, HyperSim, has a larger average depth value of 5.4 meters because they include larger and more open commercial scenes while we focus on smaller, more typical residential spaces. On average, each scene contains 55.3 objects, more than HyperSim's 49.9, and significantly more than 8020K's 19.6. Each GeoSynth scene better represents their real counterpart by containing more everyday objects and clutter. To generate GeoSynth, approximately $3,240 was spent on room preparation labor, while $2,840 was spent on compute resources to render the data. This results in only 16 cents per scene, significantly less expensive than comparable systems. For example, HyperSim estimated their costs at 67 cents per scene, over 4 times higher than ours. To show an application of GeoSynth, we trained a semantic segmentation model and fine-tuned it on the NYU v2 dataset. On the top left, we have training from scratch. Top right is training from GeoSynth. Bottom left is training from ImageNet. And bottom right is training from ImageNet, then GeoSynth. On the bottom left, we have a chart reporting the mean intersection over union performance over the test dataset. Pre-training on GeoSynth significantly improved performance over training from scratch. From ImageNet weights, GeoSynth does not improve the mean IOU score on the test dataset. Despite slightly worse average performance, individual performance for prominent classes like wall, floor, and ceiling improved. The higher performance in some of these classes results in sharper and more coherent segmentation predictions. In the zoomed-in view on the right, pre-training with GeoSynth results in better wall segmentation in low-contrast regions near the lamps and sharper segmentation near the staircase. GeoSynth is closer in domain to our deployed use case of typical modern homes. This helps correct common misclassifications that are less present in other public datasets, such as the regions around flat-screen TVs. In this visualization, we attempt to superimpose a piece of virtual art onto a wall. Without GeoSynth, the TV was misclassified as wall, ruining the illusion and possibly causing additional downstream issues with geometry regularization and lighting estimation. Our augmented reality decorating product, IKEA Creative, allows users to virtually place furniture and artwork into a 3D photo of their room. By including GeoSynth in our neural network training procedures, we were able to improve our depth prediction accuracy, our semantic segmentation sharpness, our object detection rate, and our lighting estimation model. Altogether, this results in a more immersive, higher quality experience for our users. Overall, we believe that synthetic datasets like GeoSynth can be rapidly and cost-effectively generated to provide highly representative labeled data for application-specific purposes, and that such datasets can be used to boost neural network performance in domain-relevant tasks. Thank you.